From the last video, we started seeing the maths behind some actual AI products, like in that last video, we looked at how Netflix predicts what you are going to watch next. So in this video, we'll move on to TikTok. So let's talk about the hidden math behind TikTok's algorithm. Now, TikTok has become such a very powerful social media platform for Gen Z, for young people, and I mean to the point that it's now it now has impact even on elections, on things happening in different countries and all that. So let's see, how does it behave the way it does behave. That's exactly what this video is about. So the hidden math behind TikTok's algorithm. Now, ranking systems and engagement optimization. Now, in introduction, every time a short video platform decides which video to show next, it faces a mathematical problem. So, which video should be shown to this particular user at this particular moment to maximize the value of the recommendation? That, I mean, every social media platform wants people to be glued to their platform, right? So, and for that to happen, you have to show each user what they like to watch, and so that they can watch more of it. So, a simplified recommendation pipeline is you have the candidate generation leading to a prediction, leading to a ranking, and leading to a re-ranking. This mathematics behind the mathematics behind this process draws from probability, statistics, linear algebra, optimization, machine learning, information retrieval, learning to rank, multi-armed bandits, causal inference. In this lesson, we'll build a simplified mathematical version of a modern short video recommendation system. Of course, whatever you see in this playlist is just a miniature representation of reality, because in reality, you're dealing with tons of information, billions of dimensions. So what exactly you're seeing here is just to give you a sneak peek into the reality. So let's talk about a ranking system, right? So suppose the platform has thousands of millions of candidate videos. Let the candidate set be V equals V1, V2 up to videos V1, video 1, video 2 up to the nth video. For a particular user U, the system assigns every candidate video score. So let's say S. So you have user, so that particular user U, there's a rank for of the user to each video available. So S, this corner is S of U comma VI. So you have S of U comma V1, S of U comma V2, S of U comma V3, up to S of U comma Vn, like that. So the videos are then ordered from highest score to lowest score. So the ranking can be written as V sub 1, V sub 2 up to V sub n, where V sub 1 is the video with the highest predicted value. So the mathematical goal therefore is pi star equals argmax over pi of j of pi, where pi is the possible ordering of the videos, j of pi is the utility of that ordering, how useful is that ordering, and then pi star is the optimal ranking. So you want to be sure that you have the best ranking. So the important point is that recommendation is not simply about finding relevant videos, it is about ordering relevant videos. So in 4.42 we then have the recommendation pipeline. A simplified recommendation system can be divided into four stages. Stage one, you have the candidate generation. So the system begins with a very large collection of possible videos and items and identifies a smaller set of potentially relevant candidates. For example, you have 10,000 videos leading to 10,000 candidates. Then stage two, you have the prediction. uh so you have 10,000 videos and 10,000 candidates, people that can watch. Then you have stage two. So this talks about candidate generation. The system begins with a very large collection of possible videos and identifies a smaller set of potentially relevant candidates. Then stage two, you have prediction. For each candidate, the system predicts possible user behaviors. Will the user watch? Will the user finish? Will the user like? Will the user share? Will the user comment? Will the user follow the creator? Will the user quickly skip? Those are behaviors that will be learned. So the prediction will be based on all of this. Then talking about ranking, and the predictions are combined into a ranking score, and then you have the re-ranking. The system may modify the initial ranking to account for diversity, novelty, repetition, freshness, content constraints, creator diversity, user experience. Thus, you have candidates, predictions, ranking, and then re-ranking. So re-ranking is as a result of all the modifications based on peculiarities mentioned. Then you can have a simple ranking score. Suppose the system predicts three behaviors for each video. Let's say P of W, that's probability of watching, P of L, probability of liking, P of S, probability of sharing. A simple ranking score could be score V equals W sub W, P of W, W sub L, P of L, then W of S, P of S, which are all these are weights now. So W, 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 L, W, S are all weights attached to watching, liking, and sharing. For example, the score V can then be say so. Let's say the weight attached to watching is 0.5. So 0.5 plus probability of watching, then for liking, 0.3 times probability of liking, then 0.2 times probability of sharing. So the weights determine how strongly each predicted behavior contributes to the final ranking. Then we talk about computing ranking scores now. So suppose we have three videos now, videos A, B, C, probability of watching, probability of liking, probability of sharing, like that. So you have 0.9, 0.2, and all of that. Then you can use score for score V now. You have 0.5 PW, 0.3 PL, 0.2 PS. So for movie A, to score movie A now we have 0.5 times 0.90, 0.3 times 0.2, 0.2 times 0.5, and all of that leads to 0.52. Then imagine video B, 0.57. That's the weight 0.5 times 0.7, 0.3 times 0.6, 0.2 times 0.2, and we have 0.57. So for video C, we have 0.58. So video C has the higher rank, followed by B and C. So we have CBA. Therefore, we have C greater than B greater than A. So the ranking will then be video C, video B, video A. Notice that video A has the highest watch probability, but it is not ranked first. So based on this whole thing now, video A has the highest probability to be watched, but it is not ranked first based on other possibilities. So notice that video A has the highest watch probability, but it is not ranked first. This happens because the system is optimizing a combination of behaviors. It's not just about watching, it's about all the behaviors put together. So because you want people to do everything possible on a video, right? You want them to watch, to like, and share if possible. So if you put all of that together, the most likely video to be watched does not rank high because of other factors. So you have, imagine you create videos A, B, C, then the watch probability as this, the like probability as this for each of the videos, and the share probability as this. Then you then have the video scores now. So you have the weights, 0.5 video watch probability plus 0.3 blah blah. Then the ranking, you have the ranking by sorting the values of the scores. So when you do that, in this case, you then come up, you have this one now. So video CBA is ranked first because watch probability is 0.8, like probability is 0.4, share probability is 0.3, 0. Put everything together, you get 0.5. It's just like the things we got now. So this is the Python implementation of that same thing we did, like that. I mean, why programming becomes important is maybe you're now dealing with thousands of videos, like maybe or even millions of videos now. So doing it manually also may not be the best deal. So from handcrafted scores to machine learning, you see that's where we come to. So the simple weighted score is useful for understanding the idea, but a real ranking model can be much more complicated. Represent the user, video, and context using a feature vector X UVC. All right, so examples of features include user's previous viewing behavior, similarity between the user and the video topic, video length, creator characteristics, time of day, device type, previous interactions, historical engagement, recent user activity. A simple linear model a simple linear model score is beta naught plus b1, beta naught plus beta 1 x1 plus beta 2 x2 plus beta sub p xp. So a non-linear machine learning model can instead learn score is f sub theta of x, where theta represents the learned model parameters. So the important transition is manually designed scoring leading to learned scoring function. Then you have user and video embeddings now. So another important mathematical idea is representing users and videos as vectors. Suppose the user's interests are represented by 0.8 and all this, and the video's characteristics are all this. I mean, we saw this with the Netflix situation in the previous video. So a simple compatibility score is dot product, right? So you just say 0.8 times 0.7, 0.2 times 0.1, 0.9 times 0.8. You put everything together and you get 1.30. So a larger dot product indicates stronger alignment between the user representation and the video representation. This is one reason linear algebra is so important in recommendation system. That is why even in the opening video on the mathematics of artificial intelligence, the first thing we looked at were five equations behind artificial intelligence. And of the five equations, the first thing we saw was linear algebra, talking about linear transformation, or what you can call weighted sums. like that. So here now, if we do this, we can easily calculate the dot products and we get the same 1.30 right here. And then we talk about cosine similarity. Another way to compare vectors is cosine similarity. You have cos theta is u transpose v all over this. We've come across this a lot, you know. So in that case, you use u transpose v is the dot product, and we have the length of u and v in norm u v. So cosine similarity measures the angle between two vectors. So if cos theta is approximately 1, the vectors point in similar directions. So it means the behaviors are similar. So if cos theta is close to 0, they are largely unrelated. This allows the recommendation system to compare users with videos, users with users, or even videos with videos. So you can take the vectors and do it for two videos, a user and a video, a user and a user, or even videos and videos. And that can lead to the idea of collaborative filtering we talked about in the last video. So imagine cosine similarity. You have a user behavior 122 and a video characteristic 212. So if you calculate the dot product, 1 times 2, 2 times 1, 2 times 2, you get 8 overall. The norm of the user characteristics, user behavior, you have three. The norm for the video characteristics, you also have three. Therefore, you end up having 8 over 3 over 3, which is 8 over 3 times 3. That is 8 over 9. So the vectors are strongly aligned in that case because cos theta is approximately 0.889. And that's exactly, so you can also implement that using Python here. So engagement is not one variable for sure. So a user can interact with a video in many different ways. Possible actions include watching, completing, replaying, liking, commenting, sharing, saving, following, skipping, and even reporting the video. Therefore, a recommendation system can model multiple probabilities. For example, probability of watching given U and V. That's the probability of watching. Similarly, you can have probability of liking, you can have probability of sharing. The system can combine these predictions into a broader measure of expected value. So, talking about the expected value now, suppose different actions have different values. So, watching has 1 point, liking 3 points, sharing 5 points. Then, expected value can be written as EV, which is probably watching times probability of watching, liking and probability of liking, then sharing times probability of sharing. So suppose probability of watching, liking, and sharing are all this now. You then get 1 times 0.8, 3 times 0.3, 5 times 0.1, and that ends up being 2.2. So expected value gives us a principled way to combine different possible outcomes. Then we have engagement optimization. The ranking problem can be expressed as an optimization problem. So let A represent a possible recommendation. The system seeks an action that maximizes expected reward. So we have A star to be argmax over A of the expected value of E, the ranking over all the possibilities. So R is the reward. Reward now. So A is recommended action. U is the user, and C is the context. So this equation captures the basic idea behind engagement optimization. And the system is not merely asking what video is popular, it is asking which candidate has the highest expected value for this user in this context. So it's not just about popular video. So the watch time, then talking about watch time is one possible quantity that can be modeled. Suppose the video has duration L and product probability of being completely watched equal to PC. So a simple approximation of expected watch time will be expected time, that is the L, which is duration multiplied by the probability of being watched completely. So for example, suppose video A has duration LA 60 and seconds, 60 seconds, and PC probability of it being watched completely is 0.5. So the expected value is 30 seconds. So it means that the video will be watched 30 seconds on the average. So for video B, LB is 30, PCB is 0.9. So that video will be watched 27 seconds. Under this simplified objective, video A has greater expected watch time like that. So this is greatly simplified for sure. So watch time versus completion rate now. Raw watch time and completion rate are different metrics now. So completion rate is you have watch time over video duration. That's the completion rate. Suppose a user watches 24 seconds of a 30-second video, then the completion rate is 0.80. The completion rate is 80%. So now suppose the user watches 24 seconds of a 60-second video, the completion rate will be 24 over 60, which is 0.4. The same 24 seconds of watch time produces a very different completion rate. This illustrates an important principle. Different objectives can produce different rankings like that. So let's talk about different objectives producing different rankings. Imagine you have videos A, B, C, and their duration 60, 30, 45, expected watch time 26, 27, 40.5, and then completion rate will be 60, 90, 90%. So if the objective is expected watch time, if it's expected watch time, you see that C is bigger than A, and A is bigger than B. So 40.5, 36, and 27. If the objective is completion rate, so you have, so C and B have the same completion rate for sure. So B now is equal to C, and that is, so they are both 90%, and they are both greater than A. Therefore, the ranking system must define what it is actually trying to optimize. Whatever you want to optimize is really important. So are you just concerned about watch time or completion rate? I think completion rate is better, by the way. I mean, I think, yeah, completion rate is more important, I want to think. So therefore, the ranking system must define what it is actually trying to optimize. This is one of the most important ideas in recommender system mathematics. Predictions alone do not determine ranking. So the objective function determines how those predictions are converted into decisions. Then we have multi-objective ranking. A ranking system can combine several objects. So a simplified score could be score W1 so W1 multiplied by T, W2 L, W3 S, W4 C, minus W5 K. So T, expected watch time, L, probability of liking, S, probability of sharing, C, probability of commenting, K, probability of skipping. You can combine all these things. Then the negative term represents an undesirable behavior. So you don't want anybody to skip. That's why it is taken away from the score. So a more general formulation is score of V is summation from J equals 1 to M of W sub J of probability of whatever fact feature you are dealing with there, which can be any of these things. So this is more concise. So some behaviors can contribute positively and others can contribute negatively. The weights determine the relative importance of the objective. So this W1 up to W5 determine the weights they carry. So talking about multi-objective ranking as an example now. So imagine you have a score for a particular video or something or a content. You have 0.5 T, 0.2 L, 0.2 S, and minus 0.1 K. So for video A now, you have T is 0.8, L is 0.4, S is 0.2, and K is 0.1. So you just put it all together, 0.5 times 8, 0.8, 0.2 times 0.4, 0.2 times 0.2, 0.1 times 0.1. So you get 0.51. For video B, you have this particular values. Put everything together, you have 0.545. So B is better ranked in this case because the overall score is 0.545 compared to 0.51. Therefore, B is greater than A. So video A has higher expected watch time, but video B has a higher overall ranking score. So the watch time for video A is 0.8, whereas it's 0.7 here. But putting all the factors together, video B is better than video A. For video A has higher expected watch time, but video B has a higher overall ranking score, like that. So we have this. So the same. We have the same here. You have videos A, B, C, D, the watch time probabilities, the likes, the shares, the skips, and then you set up a model for that here. Data score equals all the 0.5 times watch time, like, and blah blah. So we create all of this into a data frame here. Then if you run that, you then see that video A has the best ranking when it comes to this overall score, followed by D, followed by C, followed by A. Whereas A and C have the highest watch time, actually, but they rank the lowest because of other possibilities. So probably though they can be easily watched, well they can be easily skipped or not liked or not shared like that. So learning engagement probability. Instead of manually assigning engagement probabilities, machine learning models can learn them from historical data. And that's where machine learning comes. You don't have to explicitly put in any value. Machine learning just learns the behavior of users. So suppose the target variable is y equals 1 if engagement occurs and 0 otherwise. A logistic regression model estimates p of y equals 1, that's probability of engagement given a particular x, and that's a sigma. We have an activation function here, beta sub 0 plus beta sub 0 plus beta transpose x, where the sigma function theta of z is 1 over 1, sigma of z rather equals 1 over 1 plus e raised per minus z. So the model transforms a linear combination of features into a probability between 0 and 1, like that. So we have an example, logistic engagement prediction. So imagine z is minus 2 plus 1.5x1 plus 0.8x1, and we let x1 to be 0.8, x2 is 0.5. Putting it all together, we get z to be minus 0.4. So throw that into the activation function or the segment function. What is the segment function? You have 1 over 1 plus e raised per minus 0. Minus 0.4, and that's 1 over 1 plus e raised plus 0.4, and that's approximately 0.401. So the model predicts approximately 40.1% probability of engagement. So there's such a likelihood of engagement. We can set this up in Python. X1 is 0.8, x2 is 0.5, z score is this. Throw it into the probability machine and you get 40.01%. I mean 40.1% like we have here. Then learning to rank now. So traditional classification asks, will the user engage with this video? That's what the traditional classification asks. Ranking asks which video should appear before another video. So all the videos are there, but which one should come first? Suppose the user prefers A bit more than B more than C. The ranking model should learn score satisfying S of A greater than S of B greater than S of C. So this is the central idea behind learning to rank. So the model is evaluated not only on whether the individual predictions are correct, but on whether the ordering is correct. So this distinction is critical because recommendation systems ultimately display an ordered list. Then you have pairwise ranking. Suppose the user preferred video I over video J. So we want a score comparing a score of the user score for I, saying that it is bigger than the user score for J. Then we can define the score preference. So delta, we have delta to be S of u comma I minus S u comma J. A simple pairwise loss is then L equals minus log sigma of that difference now, where we now have sigma of this now to be 1 over 1 plus e raised to minus uh, is a grad or so. So if the preferred video receives a much larger score, then the value of that is large and positive, producing a small loss. But if the model incorrectly ranks the non-preferred video higher, then the grad becomes negative and the loss increases. Thus, the model is directly encouraged to learn the correct ordering like that. So talking about pairwise ranking loss now, if the score for movie A is 3 and score for movie B is 1, or for video A is 3, video B is 1, if the user prefers A over B, so that means that SA minus SB is 3 minus 1, which is 2. Therefore, the probability is 0.881. And then the loss is minus log 0.881, which is 0.17. Now, suppose the model gets the ordering wrong. Say of A is 1 and S of B is 3. And then we get minus 2. So the sigma becomes larger because we're going to have e raised power 2 here. And then the error will become bigger. So the sigma becomes small and the loss becomes larger. So the model is therefore strongly penalized for putting the preferred video before the non-preferred video. Now, why ranking is different from prediction? Suppose two videos have predicted engagement probabilities P of A is 0.91 and P of B is 0.90. The model does not necessarily need to predict these probabilities perfectly. For ranking, what matters is A greater than B. In other words, ranking quality is often more important than absolute prediction accuracy. Really. So this is why specialized ranking metrics such as NDCG, MAP, and MRR are important. We saw some of these metrics in the last video. Then we talk about position bias. A video shown at position 1 usually has a different probability of being watched than the same video shown at position 20. Therefore, probability of engagement given a ranking of 1 is not equal to probability of engagement given a ranking of 20. So this creates positive bias. Suppose video A receives 100,000 views and video B receives 5,000 views. We cannot immediately conclude that A is intrinsically better, Video A may simply have received much more exposure, basically. So a simplified relationship is then probability of observed engagement is equal to probability of exposure times probability of engagement given that it is exposed. Therefore, recommendation systems must distinguish between what users choose to do and what users were given the opportunity to do, because users cannot do beyond what they're exposed to. So talking about exploration and exploitation now. Suppose the system knows that a user loves basketball videos. One strategy is to continue recommending basketball. This is exploitation. But perhaps the user would also enjoy classical music. The system does not know that yet. So showing an occasional classical music video is exploration to see if they can get interested in that. Therefore, recommendation involves the trade of exploration plus exploitation. So exploitation uses what the system already knows, while exploration gathers new information. A system that never explores can become trapped in its current assumptions. So it's more like one is trapped, and that's the idea. When we talk about information spread, which I'm also interested in modeling as a mathematician, you have people trapped in echo chambers and filter bubbles like that. So because they are not open to ideas outside of their domain. So then you have multi-armed bandits. So the exploration exploitation problem can be represented using a multi-armed bandit. Imagine five recommendation categories A, B, C, D, E. Each category has an unknown reward probability. For example, the true probabilities might be probability R given A is 0.30 and probability R given B is 0.55 and so on, up to probability R given E 0.6. Initially, the algorithm does not know these values, right? So it repeatedly chooses the action, observes the reward, and updates its estimates. So that is probability of the reward you get, given that you look at you go for A, like that. So the mathematical objective so yeah, the mathematical objective is approximately the maximum value of the summation of from t equals 1 to t of r sub t. The challenge is to maximize reward while simultaneously learning which actions are best. Then we talk about the epsilon greedy strategy. One simple exploration strategy is epsilon greedy with probability 1 minus epsilon. The algorithm exploits by selecting the currently best option. So with probability epsilon, it explores another option. For example, if epsilon is 0.10, then approximately 90% of decisions exploit current knowledge, while 10% explore alternatives. So that's the epsilon greedy strategy. So probability of exploitation is 1.1 minus epsilon. Then you know, with probability epsilon, it explores another option. That's 0.10 now. So the algorithm therefore balances immediate reward against information gathering. So we see that right here. So imagine this system here. Uh, of course, we once you are going to use random. So we have random being used here. So you have to do the seeding to ensure reproducibility. So let's say the true rewards that we gathered from that system up there, all this from 0.3, 0.55 up to 0.60, we have them represented here in this list. So these are the true rewards. And then you have the number of actions. Now that's length of the true rewards. Then estimated rewards. Now you have NP0's number of actions. That's initialization here. Then you now have counts. NP zeros of the actions. So epsilon is now 0.10. So for T in range 1000, so you have 1000 situations here. So for the exploration, you have if the random is less than epsilon, then you take the action of exploration. But then, otherwise, you take the action of exploitation. So you see the argmax of estimated rewards there, and then you simulate the reward, update the estimate, then you have estimated rewards and all of that. Then you finally get the score. So the estimated rewards now you have 0.3125. We have the actual rewards, right? 0.30, 0.55, and all of that. And the last one is 0.60. So you then have estimated rewards to be this now based on the whole process. And then we have number of selections. We have 64, 21, 15, 21, 879, 879. And I think it's commensurate. Okay, it's not commensurate with these rewards now. So you have 879 selections here. So we then we go on for the cold start problem. Now, a cold start problem, like we saw in the last video, is about a new user coming to a platform or a new video introduced to the platform. So a new video has little historical information, for instance. An established video may have thousands or millions of interactions. If the system relies entirely on historical performance, established content can dominate new content. This creates the cold start problem. So a simple formulation is new item leading to little data and uncertain prediction. So a video may even have potentials to do better than the best video so far. But the cold start problem may prevent that. So exploration helps to solve this problem. So to solve the cold start problem, exploration over exploitation, because exploitation will concentrate on what's already there, whereas exploration will be open to new ideas. So the system deliberately gathers information about items from which uncertainty is for which uncertainty is high. Thus, exploration is not merely randomness, it is a strategy for reducing uncertainty. Then we have feedback loops. Recommendation systems create feedback loops. A simplified loop is you have a recommendation leading to exposure, leading to engagement, leading to learning, and then leading to recommendation. Suppose the video is initially shown to many users. It receives strong engagement. The model learns that it performs well. It is recommended more frequently. That produces additional engagement data, and then the process repeats. So you have recommendation, exposure, engagement, learning, and then it will be recommended more. So the process repeats. This can amplify small initial differences between items. So therefore, recommendation systems are not passive observers. Their decisions can influence the data they later learn from. Then we talk about the rich get richer effect. I mean, that's the reality of life most of the times. Suppose two videos have equal intrinsic quality. Initially, we have exposure A. The exposure of A is greater than the exposure of B now. More exposure can produce engagement for A. that is bigger than engagement of B. So the ranking system may then infer that the score of A is greater than the score of B. This produces even more exposure, because of the scoring, right? So more exposure goes for A. So the cycle then becomes exposure leads to engagement leads to ranking, and ranking leads to exposure. So this is one reason exploration and careful experimentation are important, because a system can tend towards exploitation a lot. That what has always worked, want to always go for it. Whereas even when something better is introduced, nobody cares. So the rich keeps getting richer, basically. That's the rich getting richer effect. Without exploration, early advantages can become self-reinforcing without exploration. And that is why it's also good sometimes. First mover advantage can also be a factor that the first item, the first thing, the first video some people see about a particular thing will most likely be the only person people are focusing on, you know. Then we talk about diversity in recommendation. Suppose the five highest scoring video are all football highlights. Pure individual ranking might produce football 1, football 2, football 3, football 4, football 5. But a user may prefer a more diverse feed. So the system can therefore introduce a diversity penalty. So a simplified adjusted score is like score prime of V is now score V minus lambda of dV, where dV measures redundancy or similarity with already selected items. So another formulation, J of L is now engagement of L plus lambda diversity of L. So the parameter lambda here determines how strongly diversity influences the final recommendation list. So we introduce that. So balancing exploration and exploitation and exploration. So let's talk about diverse penalty now. So you have video ABC with their base score and similarity penalty here. So you have score prime is now score minus 0.5 times penalty. So for score A now, you now have 0.90 still in place. Then for score B, you have 0.73. So that's like so which is yeah, 0.73. Score prime C, you get 0.80. Therefore, we see that A still remains greater than Okay, A is greater than C, C is greater than B. The system sacrifices some immediate score to reduce redundancy. So, from following the base score, A is bigger than B and B is bigger than C. But based on the similarity penalty now, we now have C doing better than B in this case. So C now does better than B. So we then move on to ranking versus re-ranking. There is an important distinction between ranking and re-ranking. Ranking simply evaluates each candidate individually. So we have score of VI. Re-ranking evaluates the quality of the entire recommendation list. That's J of V1, V2 up to VK. And the first problem asks, how good is this video? That's ranking. The re-ranking can therefore account for things like diversity, novelty, repetition, creator diversity, category balance, freshness, and user experience. This distinction is essential for understanding modern recommendation systems. Now, look at this up here. Based on the base score, we already rank ABC to be the best in that order. But based on the similarity parameter then added, we now have it now becomes ACB. That's re-ranking there because we now consider diversity in the equation. Then we have a list of utility function, right? A list utility function rather. So let L represent a recommendation list. A simplified list utility function is J of L, which is summation from I equals 1 to k of score vi minus lambda redundancy of L. So the first term rewards high quality recommendations. The second term penalizes repetitive recommendations. So the optimal list then is L star, which is ag max over L of J of L. So this formulation is more realistic than simply sorting videos according to individual scores. So it recognizes that the value of one video can depend on which videos have already been selected. So we then have a toy recommendation system. We can now construct a small recommendation system. For each video, we will define user video similarity, watch probability, like probability, share probability, and skip probability. We then combine these variables into a ranking score. The model will not produce any real platform's proprietary algorithm. Instead, it provides a mathematical demonstration of how ranking systems can be constructed. I mean, I've said that a lot, that what we are doing here is just to show for you to have a sneak peek into the reality of this thing. So whatever you're saying here is not the reality, the actual reality of TikTok, but it is like just an idea into what happens because you have tons of information on that platform. So imagine you have videos A, B, C, D, E, and you have the similarity 0.90 to 0.85. You have watch probability, like probability, and all of that set for each video like that. And then you have for the videos now, the score So you multiply the similarity by the weight 0.3, watch probability 0.3. So you do the all of that, and then you do the ranking by sorting, right? So videos will sort values of the score, and then by the time you do all of that, right, you get the values you have down here. So you then see that video E is the scores best, followed by video C, followed by video B, followed by video A, followed by video D. If all we go by is similarity, we see that C is better. C is the best when it comes to similarity, followed by A, followed by E, followed by B, followed by D. But then going by the overall score, putting everything into consideration, E comes first, like that. Then we have training and engagement model. So suppose we have historical observations of users interacting with videos. Each observation contains features such as X, similarity, watch probability, like probability, share probability, and skip probability. The target variable is this. We need Y equals 1, which is engagement occurred, and 0 otherwise. So a machine learning classifier can learn probability of engagement given a particular X, given a particular feature. So the predicted probability can then become one component of the ranking system. So in a real system, the training dataset would be vastly larger and would require careful treatment of exposure bias, temporal leakage, delayed feedback, and changing user behavior. So in this case now, imagine we have this kind of system. Uh, we use scikit-learn, taking model selection. We have a train test split. Then we have the ensemble using gradient booster classifier. Then we import NumPy as NP for numerical calculations. So for videos now, yeah, for the feature for videos, you have similarity, probability, watch probability, like probability, share probability, and skip. So we have a toy target only for demonstration, modified to allow for stratification. So this is far from reality, but we can use this, right? So imagine we now have X, we have our target 11001, like that. Then we have X train, X test. So we do a split kind of thing. So for the test size, we use 0.4 of the available information and random state for the two, and we stratify Y. Then we use the gradient boost. Now, this is totally a toy problem. So because the reality is far from this. So at the end of this day, this now, we end up getting 0.99, 0.99. That's almost 100%, of probabilities of predicted engagements. That is contrived. That's not reality, but that's the kind of how it works. So why maximize likes is too simple. So it is tempting to assume that a recommendation system simply maximizes the likes. Like the number of likes is what we are interested in. But a single metric can produce undesirable optimization behavior, like we've seen already. So a broader objective might be reward. Then you have weights multiplied by each of the parameters. W1 watch time, W2 completion, W2 like, W4 share, W5 return, which are all positive behaviors. But then W minus W6 skip, which is negative behavior. That's why it's negative here. Negative feedback, W7, which takes away from the reward. This is a simplified teaching model, not a claim about the exact proprietary objective of TikTok. So the real thing TikTok does, they know, but this is just like an idea, not maybe not necessarily the real thing. So the key mathematical lesson is the objective function determines what the system considers valuable, right? So changing the objective can change the ranking even when the underlying predictions remain exactly the same. So it depends on what you're actually looking for. Then we talk about correlation versus causation. I mean, that this is a serious debate in statistical circles, where people talk about the fact that something is correlated with another thing does not mean that it does not mean that one thing causes the other. So suppose users who watch video X frequently also watch video Y. We observe the probability Y given X is greater than probability of Y. This shows an association. It does not prove that watching X causes users to watch Y. There may be another underlying factor. Say, for example, maybe user interest X and then user interest Y. So in this case, X and Y are correlated because of a common cause, not directly because of X. So recommendation systems primarily observe behavior. So distinguishing correlation from causation is a major statistical challenge because correlation can easily be mistaken for causation, right? So for counterfactual thinking, suppose the user does not interact with a video. What does that tell us? There are at least two probability possibilities. Case one, the user saw this video and disliked it. Case two, the user never meaningfully noticed or was exposed to it. So the user may like something, but they never see it, so they won't ever interact with it. So these causes are fundamentally different. So the first gives information about preference, the second gives information about exposure. Therefore, no interaction is greater than no preference, basically. So I mean, no interaction does not mean no preference, right? So the fact that no, a video has not been interacted with does not mean that the video does not matter. It's only probably it can mean that it has not been seen by others, by people. This is why exposure modeling, randomized experiments, and causal inference are important in recommendation systems. Then we go for A/B testing ranking algorithms. I mean, as a YouTuber, right, you have the option of testing maybe the topic you are putting up for your video, how well it's going to perform, or even the thumbnail you are putting up. That's something that content creators can use a lot. So A/B testing ranking algorithm. Suppose we have two ranking systems. We have system A and system B. Users can be randomly assigned to two systems. So suppose the average outcome is Y bar A is 20.1 and Y bar B is 20.8. The observed difference is Y bar B minus Y bar A, which is 0.7. However, the difference alone is not enough. So we also need to estimate uncertainty. So a confidence interval can be written as the value we get at this del we have a plus or minus 1.96 uh, uh, standard error, like that. So A/B testing therefore combines recommendation systems with statistical inference. So that leads to A/B testing ranking algorithm. So then we have offline and online evaluation. So using historical data now. So talking about offline and online evaluation, ranking systems can be evaluated in two broad ways. We have offline evaluation, and then we also have the online evaluation. So first of all, offline evaluation. So offline evaluation uses historical data. Common metrics include AUC, log loss, precision, recall, NDCG, MAP, MRR. These are some common metrics included for offline evaluation. For online evaluation, we can deploy the model to users and measure outcomes such as watch time, completion, retention, engagement, negative feedback, user satisfaction. An important lesson is good offline performance is not the same as good online performance. So historical data were generated by an older recommendation policy, but a new model changes what users see, which changes the data generating process itself. Then we have NDCG, which is measuring ranking quality. So normalized discounted cumulative gain, or NDCG, is a common ranking metric. So first we define DCG at K, which is summation uh, from I equals 1 to K of 2 rel I minus 1 all over log of 2 into I plus 1. So here rel I is the relevance of the item at position I. The logarithmic denominator discounts lower positions. Therefore, placing a highly relevant item near the top is rewarded more strongly. So NDCG is defined as NDCG at K equals DCG at K over IDCG at K. So where IDCG at K is the ideal DCG. So in that case, we have thus 0 is less than or equal to NDCG at K less than or equal to 1, and a value close to 1 indicates a ranking close to the ideal ranking. Don't forget NDCG is normalized discounted cumulative gain. So an example of that, suppose the relevance cause of videos, right, are 3 to 1, right? So relevance cause 3 to 1. So the DCG is 2 raised power 3 minus 1 all over log 2 to base 2, like that. That's following the formula up here now. I plus 1. So the position. So we have this is 1 plus 1. This is 2 plus 1. And this is 3 plus 1. That's the position right there. That's for I. Position I is there. So here now we have 2 raised power 3 minus 1 all over log 2 base 2, then 2 raised power 2 minus 1, then log 3 base 2, then 2 raised power 1 minus 1 all over log 4 base 2, like that. So doing the DCG now, 2 raised power 3 minus 1, that is actually 8 minus 1, which is 7. Log 2 base 2 is 1, so we have that. 2 raised power 2 is 4, 4 minus 1, that you have 3. Log 3 base 2, that's 1.585, plus 2 minus 1, that's 1. Log 4 base 2 is simply half. It's simply 2 rather. So approximately we have the whole thing to be 9.393. So because the ranking is already ideal, then we have that IDCG is equal to DCG. Therefore, NDCG is equal to 1. This represents perfect ranking quality for this example right here based on this course we have. So a complete simplified mathematical model then becomes this. For user U and video V and context C, construct a feature vector X, U, V, C. So a prediction model estimates engagement P underscore U, P sub U, V is probability of engagement given that feature. Those the features you have. Then you have multiple predictions being can be combined to be R sub U comma V to be all of this now. So you have the weights with the probabilities. So additional penalties and bonuses can be introduced like this. So you have R sub UV minus lambda 1 skip, lambda 2 redundancy plus lambda 3 novelty. Finally, the recommendation list can be selected through optimization where you have L star is ag max over L of J of L. So this gives us a simplified mathematical structure for a modern recommendation system. So here we see the complete pipeline. Um, so the entire process can be summarized as user data leading to candidate generation, leading to feature representation, leading to prediction, leading to ranking, re-ranking, and of course we get the feedback. Mathematically, we have C, that's the candidates, the features of the candidates. Then we have P sub I, which is PF theta of UVIC. That's where you have the whole feature representation coming up, and then you have a score coming up at the end of the day. And finally, we get a recommendation. So the selected recommendations are displayed to the user. So the resulting user behavior generates new observations, which can then be used to update future predictions. Then the hidden mathematics we see there, the mathematics behind modern video recommendation systems like TikTok, YouTube, and all that can be viewed through several mathematical lenses. You have linear algebra, which represents users and videos as vectors. So you have user behavior as vector U, and U transpose, and video characteristics as vector V. Then the probability now, you estimate future behavior. So probability that there will be engagement given the possible features of a particular user. Then you have statistics, which estimates relationships, uncertainty, and experimental effects. Then you have machine learning, which learn complex prediction functions from a feature space. Then you have optimization, which chooses the best action. So going by agmax, and then you have learning to rank. So learning to rank, you learn an ordering that the score of VI is greater than the score of VJ, and that can actually V sub J, right? Which can help to make right predictions. And you have multi-armed bandits. You balance exploration and exploitation, right? So you don't want to just stay stuck with things you've always known. You want to be also be open to explore new ideas. So maybe the most watched video on YouTube today might be 1 billion views, but it's possible that a video can be released today and it will catch up with it over time. But if there's no exploration, that will never happen. People, the best watched video will always be the best watched video if there's no exploration, because there's a tendency towards exploitation all the time. Then you have causal inference, separates correlation. So in this case, you separate correlation from causal effect. Together, these ideas form the mathematical foundation of recommendation and ranking systems. So causal inference helps to separate correlation from causal effect. So because correlation is not necessarily causation. So putting together linear algebra, probability, statistics, machine learning, optimization, learning to rank, multi-armed bandits, and causal inference, we underpin the whole idea of recommendation and ranking systems. Then let's talk about the most important equation here. The deepest idea in this lesson can be summarized as L star equals ag max of the over L of course of expected value of reward given L comma U comma C. In words, choose the recommendation list that maximizes expected reward for the user in the current context. So this connects probability plus statistics plus linear algebra plus machine learning plus optimization. So a recommendation algorithm is therefore not simply guessing what you like. It is solving a large-scale decision and optimization problem under certainty. So that brings us to the idea, to the following key takeaways. First of all, a recommendation systems first generates candidate items, then machine learning models estimate the probability of different user actions. Ranking converts predictions into an ordered list. A ranking score can combine multiple objectives. Expected value provides a mathematical framework for combining possible outcomes. User and video embeddings allow recommendation systems to use linear algebra to measure similarity. Learning to rank methods focus on getting the ordering correct. Position bias means exposure affects observed engagement. That's the position bias there. So first video to be seen has a great likelihood of being viewed over others that come, even if those ones may be better. Then exploration allows the system to discover new content and reduce uncertainty. Exploitation uses information already learned. Then feedback loops can amplify early differences in exposure and engagement. Diversity and novelty can be introduced during re-ranking. Offline ranking metrics such as NDCG measure ordering quality. A/B testing evaluates whether a new ranking strategy actually improves outcomes. So correlation does not necessarily imply causation again. Then the ultimate problem can be represented as choose the ranking that maximizes expected utility. So the hidden mathematics is therefore a combination of prediction, ranking, optimization, experimentation, and sequential decision making. So that is TikTok sort of exposed, if you like. So important caveat here, the equations and Python examples in this lesson are educational simplification. So the commercial recommendation platforms such as proprietary systems that can involve many additional components, model constraints, experiments, and objectives. So uh, commercial recommendation platform use proprietary systems, right, that can involve many additional components, models, constraints, experiments, and observation and objectives. Therefore, this lesson should not be interpreted as a reconstruction of TikTok's exact production algorithm, not at all. We're just trying to talk about the mathematics, behind that. Instead, it provides a mathematical framework for understanding the kinds of problems that large-scale recommendation systems must solve. What should we show? To whom should we show it? In what order should we show it? What outcome are we optimizing? How do we learn from what happens next? Those five questions lead directly into modern recommendation systems, ranking algorithms, machine learning, and optimization. So when now we come for the practice problems. Here, solve the following problems using the mathematical concepts developed in this lesson. Show all important steps and explain your reasoning where appropriate. So, in this case, I'll have to solve two problems. Those will be uh problems 15 and 18. So here you can see problems 1 and 2, all of them. Problems 1 and 2 clearly here. Then you have problems 3. Okay, let's focus on 3 alone here. 3, then 4, 5, then 6, 7. Okay, yeah, 7, 8, 9, 10, 11, 12. Okay, I think we can see 12 and 13 here. 12 and 13, 14 and 15. 14, can we see 14 and 15? Yeah. Okay, let's do 14 alone. 15 is not showing in full. So this is 14. This is 15, talking about regret. Suppose the true reward probabilities of three recommendation strategies are 0.4, 0.55, 0.7. The system chooses A for 200 rounds, B for 300 rounds, and C for 500 rounds. So the optimal strategy would have selected C every time. So calculate the expected reward of the actual strategy, calculate the expected reward under the optimal strategy, calculate the expected regret. So I'll be solving that. Then we have, so I'm solving 15 and 18. Then 16, diversity aware re-ranking. Four videos have initial value scores. The initial scores that. So we did something like this in the lesson. So you want to try this. Then 17, you have 17 right here. Then you have 18. So I'll be solving 18 also. Two ranking systems produce relevant orders for four videos. So the true relevance values are 3210. System A ranks them as 3210. System B ranks them as 2301. And then calculate DCG at 4 for both systems using DCG at K. So using that formula, which system performs better? So we can decide that. I'm going to solve that too. So 19, you have 19 right here. Talking about A/B test confidence interval. Then 20 finally. Yeah, so let's go ahead and solve 15 and 18 as we call it a date. So 15. So problem 15. So from problem 15, From the question I read out the other time, the true rewards, the true reward probabilities, the true reward probabilities are P of A equals 0.40, P of, sub B is 0.55, P sub C is 0.70, and then the system the system selects A for 200 rounds, B for 300 rounds, and C for 500 rounds. So you can say, therefore, the expected reward of the actual strategy, of the actual strategy is, we're talking about expected reward. So expected reward for the strategy. So expected reward is equal to 200, 200 going with 0.4, then 0.55, 300, 0.70, 500. That's the actual, the expected value. So that's 200 into 0.40 plus 300 into 0.55 plus 500 into 0.70. So that is 80 plus 165 plus 35 plus 350, I think. Yeah, 350. Yeah, 350. So all of that goes to 595. So that's 595. So that's 595. So we can say that the optimal strategy, okay, the optimal strategy always, the optimal strategy always selects C. You can see the value of C. I mean, sorry, C is so you see C is 350. The optimal strategy always selects C because 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 we see PC, because P sub C is 0.70, is the highest reward probability. Reward probability. Again, we know that there are there are 200 plus 300 plus 500, which is equal to 1000. So there are 1000 rounds, 1000 total rounds, like that. Therefore, therefore, the expected reward, the expected reward under the optimal strategy. Under the optimal strategy is the expected value of R optimal. That'll be the total number of rounds multiplied by the probability, the highest probability, which is equal to 700, like that. So then the expected regret, the expected. So three questions were asked. We're asked to find the expected reward for the actual strategy. We have that. But for the optimal strategy, we go for the biggest probability. So, and that will be applied to everything. That will apply to the total rounds. So the highest probability. So that gives us the expected value of the optimal strategy. So the expected regret, which is the last thing to compute, the expected regret is given as regret equals the expected value of the optimal strategy, R optimal, minus the expected value actual of the actual strategy, ER. So that's what the regret is. That's more like the loss kind in a way of thinking. So regret then is equal to, so E optimal is 700, then ER is 595 like we computed already. So that tells us that the regret is equal to 105, like that. So 105, that's the regret. So here we see that the recommendation system loses an expected 105 reward units because it sometimes chooses strategies that are inferior to the best available strategy. That's why we have that regret. So this illustrates the central exploration exploitation problem. Choosing a seemingly weaker option can reduce immediate reward, but exploration may produce information that improves future decisions. So that's the kind of thing we have there. So let's go on to problem 18. So problem 18 now. So in problem 18, we have the true relevance values. The true relevance values to be 3, 2, 1, and 0. Then for system A produces the ideal ranking, the ideal ranking 3, 2, 1, 0, and system B produces 2, 3, 0, 1, like that. And we have the DCG formula. The DCG formula is DCG at K equals summation from I equals 1 to K of 2 relevance I minus 1 all over log to base 2 of I plus 1, like this. So we go system by system. So for system A, we have DCG at A, and that is now for A, right? We have 3210. So just like the original relevance values, 3210. So for DCG, we have 3210. So don't forget 3210. So for the positions now, this is first, second, third, fourth, because those also matter. So now for DCGA, So that's DCG at A. That is then 2 raised to power the relevance 3. That's 2 raised to power 3 minus 1 all over log to base 2 of the first position. The position is 1. So we have 1 plus 1. So position 1 plus the 1 that was there before. We have that. Plus, next, we have 2, 2 raised power the relevance. So that's 2 raised power 2 now, minus 1, all over log to base 2 of this one is in position 2. So we have 2 plus 1, then plus the next one, that is this, that's 2 raised power 1 minus 1 all over log to base 2, 3 plus 1, like this. Then finally, we have 2 raised power 0, this relevance score here, minus 1 all over log to base 2, 4 plus 1. So if we take all of that together, we then have DCG. DCG at A to be 2 raised power 3, that's 8 minus 1 all over log to base 2 of 1 plus 1, 2. Then plus 2 raised power 2, that's 4 minus 1 all over log to base 2 of 3. Plus 2 raised power 1, 2 minus 1 all over log to base 2 of 4. Then plus 2 raised power 0, 1 minus 1 all over log to base 2 of 5. So with that in place, we have DCG at A to be equal to, this is 7, log 2 base 2 is 1, plus 4 minus 1, 3. We have log 2 base 3, log 3 base 2 rather, then plus 2 minus 1, that's 1 all over log 4 base 2, that's simply 2. Then 1 minus 1, that is 0 over log 5 base 2. So then we have DCG at A to be 7 plus 3 over log 3 base 2 plus 1 over 2 plus 0. So we can say since since system A, since system A has the ideal ranking, has the ideal ranking, since system A has the ideal ranking, we can say that IDCG is equal to DCG sub A, like that. So because we already have values well above 1 here. So we then go for system B. So for system B, right, we have 2301 or something like that. Yeah, 2301. This for system B, 2301. So we have 2301. These are the relevance scores, and then the positions 1, 2, 3, 4, like this. So we can then have DCG at B, DCG at B equals, so we have from the formula, this is 2 raised power 2 minus 1 all over log to base 2 of this one here, 1 plus 1 plus 2 raised power 3, this 3 now, minus 1 all over log to base 2 of the second position now plus 1 plus 2 raised power 0, this one, minus 1 all over so log to base 2 of 3 plus 1. And lastly, 2 raised power 1 minus 1, this one now, all over log to base 2 of the position 4 plus 1. So we have all of that. And then we have DCG at B will now be equal to, so 2 raised power 2, 4 minus 1, that's 3. Log 2 base 2 is 1. Then 2 raised power 3, 8 minus 1, that's 7. Then log 3 base 2. Then plus 2 raised power 0, 1. 1 minus 1, 0. 0 over anything is 0. 2 raised power 1, 2 minus 1. That's 1 all over log 5 base 2. Like this. So that tells us that DCG at B is equal to 3 That's 7 here. That's 3. Sorry. That is 3 plus 7 over all of that. Um, let's see what's happening here. 3 over 1. We have that 7 over log 3 base 2 and 0. Okay. So we have 3. 3. Okay, yeah. I think we can so now we want to compare the two basically here. So we have that. So don't forget what this is what we brought from this is what we brought from DCG of A like this. And then for DCG of B, this is what we have here. So let me just write that out a bit better. DCG at B is now 3 plus 7 over log 3 base 2 plus 1 over log 5 base 2 like this. So finally, DCG at B is so for DCG at A, we can finalize this, right? This is DCG, DCG, DCG at A is approximately 9.393. 9.393 for DCG at A. For DCG at B, so we can also conclude that. So that is approximately 7.743. So next we can calculate now, now calculate, calculate NDCG. So to calculate NDCG, we have ND, so we have NDCG at B is DCG at B over IDCG. That is simply 7.743 all over 9.393 because that was the ideal, all over 0. I mean, that becomes 0.824. Then NDCG at A, we take that as the ID because it is the bigger value. So that will be 9.393 all over 9.393, which is equal to 1, like that. So in this case now, our conclusion is that system A system A performs system A performs better because the most because the most relevant because the most relevant videos appear at the highest positions positions. So the important lesson is that ranking metrics care about where relevant items appear, not merely whether the correct items are present. In a short video feed, this is crucial because users are much more likely to interact with items near the beginning of the ranked list. So with this, we come to the end of this important video about the TikTok algorithm. So I'll flash the questions once again, and then it will be over. So here we have okay, let me just show the problems now. So we have 1 and 2. Okay, we should be able to have 1 and 2 together, yeah? You can see all of 1 and 2 like that. Then 3 and 4. Can we do 3 and 4 together? Okay, that's too small. So let's focus on 3. So we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, which I did. I did 15, then 16, 16, 17, 18, which I also answered. And we saw system A performing better, putting things in the right position. Then 19 and 20. Let me know how helpful this is for you. And if there's something else you'd like me to try to talk about, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. If you haven't subscribed, it is a good time to go ahead and subscribe. And of course, you want to click on the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join, which gives you some special privileges you find out as you click on join. Um, Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Um, Till I see you again, keep doing maths right. Bye.